أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله. Welcome back. Today we have a problem on simple circular motion. Let us read it as usual and find a solution to the problem. It says a phonograph record rotates at 33 whole number 1/3 revolutions per minute. A express the angular velocity of the record in radians per second. B says, what is the speed of a ladybird sitting on the record at a distance of 5.0 centimeters and at a distance of 10.0 centimeters from the center, meaning from the center of the phonograph record. First of all, a phonograph record is a circular material and it is rotating, okay? It is rotating, and that is why it is involved in the study of simple circular motion. And we apply the physics of circular motion to the phonograph record. Okay, taking the first part of the problem, and it says express the angular velocity of the record. So what is angular velocity? We need to ask ourselves this question, what this angular velocity is all about, and that they say we should express the angular velocity in radians per second. Okay, we will begin this by explaining the angular velocity. Let's say we have a circular tract. Let's say we have a circular tract, okay, and then this is the center of the circle. We can name this center of the circle O. If I draw a straight line from the center to this track, the distance from here to here is called radius and is given the letter R. Let's say I have let's name this one A, and let's say I have an object here, or let's say we have a car here, okay, and it is moving in this direction. It moves in this direction. Now after some time t seconds, let's say the car is now in a new position, and I'm going to call this position position B here. This is where it is after t seconds. I can draw another straight line from B to O, and the two lines are equal. OA and OB are equal. Each one is radius. Then clearly we see that by moving from A to B, it formed an angle at the center, the angle in this direction. You see that? This is the angle theta. Now I can measure how much of this angle is formed in 1 second. Okay, the measurement of how much of this angle is formed at the center while the car is moving round the track, this measurement is what we call angular velocity. How much of this angle is formed in 1 second. So it means after the time t seconds, when it formed this angle theta, our angular velocity denoted by omega is equal to the angle formed at the center theta divided by the time taken to form this angle t. This is the formula we use to calculate angular velocity. The angle here is not measured in degrees, it's measured in radians, and when the time is measured in seconds, okay, it means we can measure angular velocity in radians per second. And the short form of writing radians per second is to take the ARD here. So this is radian, then you write it like this per second. This is how we write it, the unit of angular velocity, radian per second. Now here is something important. If the car moves from here past B and then backs to A again, it has completed 1 revolution. So it has completed 1 revolution, and this 1 revolution is equal to the angle formed here is, for every 1 revolution, the angle formed is 2 pi radians. This is very important. 2 pi radians. Their theta is 2 pi radians, and the time taken to make 1 complete revolution is a special time in physics, and we give the name period to the time, and we differentiate it from the usual time that we have here. We give it a capital letter T. Capital letter T stand for period in second, and is the time taken to complete one revolution. To move, if it started from A, then the time taken to move around this track and then comes back to A again. Or if it started from B, then the time it takes to move around and then come back to B eventually. That time is period and is given capital letter T. Okay, remember what we just said. When it has completed one revolution, the angle is 2 pi and the time is capital T. So my angular velocity, I can also use this formula and say, okay, 2 pi when it has completed one, that's my angle when it has completed one revolution, and the time, you see, your angle is 2 pi, I'm just transforming this one, your angle is 2 pi, and then the time taken is period capital T. So I have another formula for calculating angular velocity, that angular velocity is equal to 2 pi upon T. Now, there is also what we call angular frequency. Angular frequency. This angular frequency is denoted by small letter f and is the number of revolutions it has formed or it made in 1 second. How many revolutions in 1 second? If we say the angular revolutions is 20 revolutions, angular frequency is 20 revolutions per second. What we mean is in every 1 second it will make 20 complete revolutions. 20 complete revolutions. If we say it's 1.5 revolutions per second, then we mean in 1 second it has made 1.5 revolutions. That's the meaning. We call this angular frequency. Now the frequency is related, these two here, the frequency and the period, are related by a formula that say f if f is equal to the reciprocal of t. So if you know the period, then 1 upon the period will give you the frequency. So going back to this formula, we see that we can transform the formula in another way. Our omega is 2 pi upon t. I can say, okay, this is 2 pi into 1 upon t. I just transformed it. I can just say 2 pi times 1 and I will get this back. But the significance of this bracket is that it has 1 upon t, and this formula tells me that 1 upon t is f. So instead of this 1 upon t, I can say 2 pi f. You see that? 2 pi f. In summary, it means I have about 3 different formulae for measuring my angular velocity. First of all, I can say omega is equal to theta over t, and this is the first equation. Second of all, I can say omega is equal to 2 pi upon capital T. Capital T is the period. That's the second formula for calculating omega. Finally is this one I've just got, which is omega is equal to 2 pi f. You see that? If I know this theta and I know t, I will get the omega from here. If I am given the period and they say calculate omega, I will just say omega is 2 pi over the period given. But if I am given angular frequency, how many revolutions it has made in 1 second or in 1 minute, then I will use this equation 3. This is the third one. I will use equation 3 to get my omega. So we are going back to the problem and see which one we should use out of these 3 equations. Okay, if you read the problem, it says a phonograph record rotates at 33 whole number 1 upon 3 revolutions per minute. Now this is significant. I like this. Revolutions per minute tells you that This is angular frequency. It means your frequency is 33 1 upon 3 revolutions per minute. This is how it is abbreviated. You are given angular frequency, and this means that I am going to use equation 3. I'm not given period, so I will not use this. I'm not given the angle form at the center. I'm the time taken to form the angle, so I will not use equation 1 either. I will now resort to equation number 3. Okay, but this my frequency here is not in the SI unit. The SI unit should be uh, revolution per second. Okay, revolution per second, but it's not in the SI. So what I will do is I will convert that. But never mind. My frequency should be equal to 33 1 upon 3 uh, revolutions. Okay, revolutions, but this is per minute. I am given, they say per minute, so I will say divided by 1 minute. So this is equal to what I will have now is I have 33 1 upon 3 divided by 1 minute is 60 seconds. So I simply change this one to second. 1 minute is 60 seconds. Let me cancel this, and this means I have it in revolution per second. That is my frequency. Finally, I will now say omega is equal to 2 pi f. So this will now be 2 pi, meaning I am taking this formula 2 pi, and then my f is the whole of this, so I will have times 33 1 upon 3 divided by 60, and once I do that, it is now in radian per second, the unit of omega. Why did I change it to radian? Because every one revolution is 2 pi radian, so I have to remove the revolution, and if you see my formula here gives me the 2 pi, so I don't need this one now, so I have radian instead, and then the second is from the 60 here. I change 1 minute to 60 seconds. Okay, now how do I find the answer here? Okay, here is the thing. So I will say this is equal to 2 pi multiplied by, I will convert this one to improper fraction. I will say 3 times 33. This will give me 99 plus 1. Okay, and this will be 100. So I have 100 divided by 3, and then everything here divided by 60, and this is in radian per second, and this is equal to, okay, I will now bring this to be multiplied by the 30 under. So it means in the numerator I have 2 pi multiplied by 100 divided by, then I have 60 multiplied by 3 in radian per second. So I will open bracket here, close bracket, open bracket, close bracket. Okay, then I bring my calculator. For the numerator, I open bracket, okay, and press 2. If I want pi to appear, I will press shift, press this one, then the exp, exponential, and you see 2 pi appears. Then you say multiplied by 100, and then now you can close bracket here. You see close bracket. After that, then you press the division operator, and then you open bracket again. If you open bracket here, then you have 60 times 3, then you close bracket. 60 times 3, you close bracket, and now you press the equality sign, and this will give you the angular velocity in radian per second, 3.49, correct to 3 significant figures, and you have 3.49. This is in radian per second. With this, you have successfully solved a part of the problem. Now, this is my angular velocity. Now, How do we solve the second one? How do we solve the second one? It says, what is the speed of a ladybird sitting on the record at a distance of this and then this? Okay, this will now take us to a new formula. Uh, Let's establish that formula before we proceed. It is a relationship between angular velocity and linear velocity. Remember, I said that when the object, such as a car, travels from A to B, it takes time t to form the angle at the center, theta. Now it takes the same time to cover the distance from A to B. From A to B, you have a distance here, this line, this arc here, the path it follow. Let's give it a letter S. You see, now it takes t seconds to form this distance, and same t seconds to form at the angle theta. Okay, provided this theta is small and it is measured in radians, then the distance S, the angle theta, and the radius are related by this formula. S is equal to r theta. Now, since the time taken to form this theta is the same as the time taken to form to cover the distance S, which is t, I can divide both sides by that time. So I will say divided by t here, divided by t here. Now, since this one is distance over time, clearly you can see this is linear speed or linear velocity is equal to, and then this theta over t, can you see, is r omega. We say omega is theta over t. So this means if I come back to this formula, I will have r omega. You see, v is equal to r omega, where this one is linear, we call it linear velocity, okay, and then omega is angular velocity. This means there is a relationship between linear velocity and angular velocity. If you know angular velocity, you can simply multiply it by the radius of the circular track to get the linear velocity. In other words, if this angular velocity increases, the linear velocity will also increase when the radius is constant. Sometimes the angular velocity is constant, but you have, when you are considering different positions, then you have different values of r, and then v is different for different values of r. When r is large, v is large. Okay, in the second problem, we are going to use this formula. Okay, but coming back here, if I have a ladybird, as they said here, you have a ladybird sitting on the record at a distance of on the record at a distance of 5.0 centimeter. Okay, I'm going to assume that the 5.0 the whole of this is the record. Okay, the whole of, and is rotating. So let's say I have a bird, and the bird is somewhere here. You see, somewhere here, and the distance from here to here, you see, the distance from here to here is 5.0 centimeter. This means my r, you see, if it is rotating like this, the bird will now have its own circular track. You see, this is the circular track for the bird, and definitely this is the radius of the circle. So it will have its own velocity, linear velocity, but the angular velocity remains constant. So how do we find this v? I'm going to call this v1, and the r, this 5.0 centimeter, I'm going to call it r1. Again, how do we find it when it is 10.0 centimeters from the center? This is the center. Let's say it is not here, it is somewhere here, here. So it because 5.0 is 10.0 is more than 5. So when it is somewhere here, you see the radius has increased to 10, and then you have r2 as what, 10.0 centimeter. Okay, simply this is what we are going to do. For B, we will say, okay, our R1 is 5.0 in centimeter, and then we have to divide this by 100. 5.0 divided by 100, this will be 0.05 in meters, because it has to be in meters before we use it to solve problem. R2 also is 10.0 in centimeters, and we have to divide it by 100, and this will give us 0.10 in centimeters. Sorry, in meters, not centimeters again. Okay, to find for Roman number 1, if we want to find the velocity, we say V1 is equal to R1 omega. V1 equals R1 omega, and this is equal to our R1 is 0.05, so I will say 0.05 multiplied by our omega. We calculated the omega is 3.49, so this is 3.49, and then we bring our calculator and simply say 0.05 multiplied by 3.49, and this will give us the angular. This will give us, you see, that's something like this, 0.17, correct to 2 decimal places, 0.17 in meters per second. Okay, if I want to get the other one, I will just say, okay, my V2 is equal to R2 omega. Remember, omega is the same for all of them. My R2 is the 10 centimeter distance, okay, the 10 centimeter, which I change it to 0.10. So this will now be 0.10 multiplied by omega, and my omega is 3.49. okay, if I do that, let's see that quickly. 0.10 multiplied by 3.49, and this will give us 0.349 to 2 decimal places. This is approximately 0.35 in meters per second. You see, the linear velocity is in meter per second, but the angular velocity is in radians per second. I hope this is clear to all of you. Assalamu alaikum wa rahmatullah.